This work is called Haven, and it's about shielding applications from an untrusted cloud. So in the good old days, when you wanted to run an application, you went out and bought a computer, and you put your application on it, and you put an OS on there as well to support the app. And sure, they were probably full of bugs, but you controlled and managed all the software on the machine. And so you were reasonably confident that the only bad stuff you had to worry about was on the other side of a network. And so as long as you secured that interface really well, you are often comfortable in using a system like this to manage your secret data. In the cloud, however, it's quite different. Obviously, bad stuff still comes in from the network, so you need to control that interface. But you should also assume that there's malware running in the cloud. And if it can compromise the cloud provider's platform, then it can mess directly with your VM, regardless of how well you secure the network interface. And there's nothing you can do about it. This isn't just a theoretical concern. Just over a week ago, Amazon finished rebooting all the EC2 nodes to correct a privilege flaw in Xen that could have resulted in just such a data compromise. In this talk, I'm going to present a system called Haven that achieves completely secure private execution of unmodified applications like SQL Server and Apache in a completely untrusted cloud environment on commodity hardware. And the hardware, the commodity there comes with a little asterisk. The hardware we use is something called Intel SGX, and I'll talk more about that in a minute. But to motivate the problem a little bit more, the real fundamental problem here is that the trusted computing base of the cloud is enormous. It includes all of the privileged software on the machine where your application runs, like the hypervisor and firmware and so on. It also includes the cloud provider's management stack that has control over that privileged software, and a whole lot of people, either staff that have administrative privileges on the hardware or staff with physical access to the hardware, like cleaners and security guards. And finally, as the Snowden leaks have reminded us, you should also consider law enforcement bodies in any jurisdictions where your data might be reached or replicated. And the fundamental problem with this is the hierarchical security model that we use to build computer systems. Because we have a hierarchy of trust, any of the layers at the bottom of this stack can observe or modify any data at layers above them in the stack. Even if your application always encrypts its data before storing it to disk or sending it over the network, as soon as you decrypt data in memory to compute on it, it's vulnerable to compromise. So what can we do about this problem? Well, the state of the art in industry today is probably hardware security modules. These are dedicated crypto appliances that you can rent, and so they're fairly expensive, and they implement a limited set of APIs basically just for storing your keys and for performing crypto operations like signing and encryption and decryption. And so these are great for protecting your crown jewels, your high-value crypto secrets, but they're not really good for general-purpose computation. The other approach that people have looked at in research is to use a very small, hopefully secure hypervisor or microkernel environment. And because this is small, you can have a greater confidence in its correctness. It has a smaller trusted computing base, and it ensures some basic security property like strong isolation between its guests. There are a bunch of problems with this approach. The first is that you need some sort of administrative interface for people to control the behavior of the machine, and they often allow for access to guest data. The second problem is because these are running on regular unmodified hardware, that they're still vulnerable to a wide variety of physical attacks, like simply reading secrets out of memory. And the third, perhaps apparent problem, is how do you know that some machine somewhere in the cloud is actually running the small secure hypervisor that you expect it to run? Of the three, this one is actually a solved problem. And it's solved by a mechanism called remote attestation. So if you already know how this works, feel free to go to sleep for 30 seconds. The basic idea is that at boot time or sometime early on, you construct a secure hash of all the privileged software running on the machine. And this is then signed by a small piece of trusted hardware like the TPM chip. And some remote user checks this measurement, both the hash and the signature chain, before deciding whether to trust that remote machine. So the basic idea here is not preventing the wrong software from running, but making it possible to detect when the wrong software runs. The problem with this is great, this works, but the problem with it for the cloud scenarios is, how do you know what this expected measurement, what this hash value is going to be? If we assume that the cloud provider has to be free to patch and update and modify their privileged software at will, which all cloud providers today do, then what this boils down to is basically trusting the cloud provider to tell you the expected hash of their privileged software. And that's not very satisfying. So let's stop and step back for a second. What do we really want from the cloud? There's an older alternative to running things in the cloud, and it's called a secure colocation provider. The basic idea is you configure the hardware and software the way you like, the way we did at the example at the very beginning, and you place it in a locked rack. And the colo provides power and cooling and network access, and nothing else. So they can always withhold resources, they can switch off the power, or if they're malicious, they could try to attack you through the network interface, but they can't otherwise get at the data inside your machine. We'd like to have a similar guarantee for execution in the cloud. So have the cloud provider limited to providing raw resources and untrusted I/O channels, and nothing else. And then if we get this right, it doesn't matter what the provider's privileged software looks like or what it does, because it's outside our trusted computing base from the perspective of the guest. More specifically, more concretely, we've termed this property shielded execution. And the basic idea is protecting a specific program from everything else on the system, regardless of how privileged it is. So you think of this like an inverse sandbox, where the stuff you care about is inside the sandbox. The other wrinkle that makes this particularly challenging is that the program we're trying to protect is an unmodified existing application. So it's really naive to the existence of the sandbox or what threats there might exist outside it. And despite that, we want to protect both the confidentiality and integrity of the program itself and all of its intermediate state, control flow, register values, etc. And so if we get this right, the program can compute on encrypted inputs and produce encrypted outputs, and all of the intermediate state and all of the data it operates on will remain confidential. And in general, the host can always deny service. It can choose not to execute the program or limit the resources it gives to the program. But if the program produces outputs, it can't alter the behavior of the program. In this work, we assume an actively malicious cloud provider. We do that not because we think that real cloud providers are likely to be malicious, but because it's a real convenient proxy for real threats, such as a motivated inside attacker, or perhaps the cloud provider being compelled through a subpoena to divulge user data. We assume that all the provider's software is malicious, and all the hardware beyond the CPU package itself is untrusted. And so that admits a whole variety of interesting attacks like DRAM snooping and cold boot attacks. We do not prevent denial of service. In the cloud scenario, I claim this isn't an issue. If you're not getting the service you'd like, well, don't pay them. And we don't handle side channel attacks. That's an open issue. So I said that we were building on top of some hardware called Intel SGX. Let me tell you a little bit more about that. SGX is a new architecture extension for isolated execution. It allows an application to construct a region of its virtual address space known as an enclave, and it can put secrets and code that operates on those secrets into the enclave. And the hardware ensures that nothing else on the system can mess with them. Even though it can trivially corrupt the rest of the application, the only way it can get into the enclave is through the code that's inside the enclave. SGX also includes a remote attestation mechanism, much like the TPM example I mentioned earlier, so that a remote user can verify that exactly the software and only the software they expect is running inside the enclave. At the hardware level, I don't have time to talk about all the details, but briefly, an enclave occupies a contiguous region of virtual address space, and the pages that make up the enclave are backed by a specific region of hardware encrypted and integrity protected physical memory. The hardware also ensures that the OS can't mess up the page table mappings underneath the application, so the application always knows that it's seeing the same data at the same address. And it protects the enclave's register file. So when an exception or an interrupt occurs, it protects the OS from seeing that. And it provides a secure control transfer mechanism, a little bit like a system call to execute inside the enclave. So this is pretty powerful stuff. Are we done? Well, SGX is great if you're willing to split your application into a small trusted piece and the big untrusted piece outside the enclave. But if we want to execute a completely unmodified application, there are a couple of challenges. First, there are technical challenges to simply executing that much code in the enclave. But the bigger issue is what we know as Iago attacks. An application isn't an island. It depends upon an operating system and assumes the operating system is correct. And it interacts with the operating system through a wide, rich, and pretty complicated system call interface. And because the application assumes the OS is correct, these system calls provide the perfect way for privilege level malware to corrupt the behavior of the application. There are many different forms of Iago attacks. To give you just a couple of examples, Malloc might return a pointer to the user's existing stack, causing the user to overwrite their return address. The scheduler might allow two threads to race into a mutex when they think they're protected against mutual exclusion. System information might report spurious values, causing the application to dereference an invalid array index. Or simply system calls might fail with errors that you don't expect. I'm sure you can imagine many, many more of these just with a few minutes of thinking. And so our approach is, because this interface is so rich, it's not tractable to try to check all of these possibilities. Instead, we admit all of the pieces of the OS that the application directly depends upon to provide these kinds of system call semantics into the application's trusted computing base. So in our system, called Haven, we construct a Pico process, which is an isolated user mode address space. And inside that, we construct an enclave. And inside the enclave, we load completely unmodified application binaries. They depend upon the Windows 8 API. And that is provided by a library OS called Drawbridge, which is previous work. And Drawbridge is essentially, Drawbridge is a subset of Windows that's enlightened to run in process with the application. It provides all of the semantics that the application depends upon, but it still relies upon a small set of core OS primitives. And it assumes that they're implemented correctly. So to implement those, we introduce a new piece of code called the shield module. That implements typical kernel functionality like a scheduler, virtual memory management, and a file system in terms of a much smaller and much narrower, untrusted interface with a host OS. So I'm going to talk in a little bit more detail about these two pieces, but combined with a small amount of untrusted code outside the enclave, we've now ensured completely mutual distrust between the application inside the enclave and the host, the cloud provider's host OS. So the untrusted interface, this is this key interface at the enclave boundary that's responsible for ensuring mutual distrust. And we designed this interface using a twist on the old idea of policy mechanism separation. In Haven, the guest controls all policy over virtual resources. So by virtual resources, I mean things like virtual address layout, threads, thread scheduling, and so on. However, the host still controls all the policy over physical resources like pages, time on vCPUs, or time on physical cores, because the guest is, after all, being paid for a certain amount of physical resources and it needs to retain control over that. The untrusted interface consists of about 20 calls with fairly restricted semantics. The details are in the paper. And on top of the untrusted interface, we have this block of trusted code known as the shield module that is responsible for then implementing all the things that our library OS and our application need. It includes a memory allocator and a region manager. So when the application says something like malloc, what this ultimately boils down to is that the shield module actually chooses a virtual address region. It knows the enclave's virtual address layout. It decides where the pages are going to go, and it issues calls to the untrusted OS saying simply, place a page at this address with these permissions, please. And then it verifies through a hardware mechanism that the OS did the right thing. No address allocation is in the OS, so we don't need to encode complicated semantics about what addresses are valid inside the enclave. The shield module also implements a private file system. This is currently implemented as a FAT file system on top of an encrypted and integrity-protected VHD. So the untrusted OS only sees block-level reads and writes of encrypted data. It implements a scheduler because we don't trust the host OS to schedule our threads, not just to manage mutexes, but even if we controlled that, we don't trust it to perhaps allow two different threads to control their thread interleavings to allow people to enter benign race conditions that exist inside the application. We don't want to open up that possibility to the untrusted OS. So instead, we implement a scheduler, much like scheduler activations or upcall scheduling inside the shield module. The shield module also is responsible for handling exceptions like page faults and for emulating some instructions like CPU ID that can't be executed inside the enclave. The shield module also has a general policy of sanity checking all the untrusted inputs that come in from outside the enclave. So much like an OS kernel is supposed to sanity check all of the system call parameters, the shield module does similar checking on the return values from system calls. However, its job is a little bit easier because if it sees anything wrong, we allow denial of service. So we treat this as a denial of service attack and we simply panic and stop executing the enclave and terminate the process, rather than allowing it to continue in an unknown state. The Shield module currently consists of about 23,000 lines of code, but more than half of that is the fat file system implementation that we use. So we've built Haven, and in doing so, we identified a number of limitations in SGX, which is hardly surprising because SGX was designed to protect small pieces inside of applications, not complete applications on library OSs. The first and the most glaring issue is dynamic memory allocation and protection. We obviously need to dynamically allocate pages and change the protection of those pages to handle things like malloc. And in order to do that on SGX, we basically require new instructions that allow the guest and the host to cooperatively add memory to the enclave. The second is exception handling. Some types of exceptions, including page falls, weren't reported to the enclave, allowing the enclave to handle them. The third is permitted instructions. There are some instructions, particularly reading the timestamp counter, that can't practically be emulated inside the enclave. And the final one is another sordid tale about thread local storage on x86. You can read the paper for details on that. The fantastic news is that all of these problems are fixed in a new version of the SGX spec that I don't believe has been published yet, but will be real soon now. The paper also includes a bit of a discussion about future performance optimizations and things that could be done to make SGX even better. But the great news is that Haven would work with this new version of SGX. So performance. I'm not going to give you a very detailed performance evaluation. And that's because although we implemented and tested Haven using a functional emulator for SGX, we didn't have access, and we don't have access to a real SGX implementation, so we can't make performance measurements on real hardware. Instead, what we did was construct a model for SGX performance, and basically this model consists of flushing the TLB every time we enter or exit an enclave, and that's required by the hardware, and then simulating the overhead of the actual SGX instructions with a variable delay, and simulating the performance penalty of the access to encrypted memory by slowing down the system's overall DRAM timing. And so obviously when you have a model like this, then the performance of the system depends critically on the numbers that you put into the model, and we really don't know what those numbers are going to be. So I'm not going to talk you through all the different parameters, and the details are in the paper. But if I pick one hopefully pessimistic set of numbers, which is that all the SGX instructions take more than 10,000 cycles, and RAM as a whole, not just encrypted memory, is 30% slower overall, then we get a slowdown versus a typical virtual machine configuration of somewhere between 1/3 and 2/3 for Apache and SQL Server. And that's, a significant slowdown. But I think even today, even with a performance result like that, remember that you don't have to trust the cloud. And this is pretty exciting, and I think this is already something that a lot of users would be willing to accept. So what's next? The paper obviously goes into more detail. The biggest class of attacks that Haven doesn't currently defend against is rollback of persistent storage. When we recover from a crash, we can't tell if we're reading the most recent version of the encrypted VHD image that was written. And fixing that requires either more hardware or communication with trusted hosts on the network that can provide us that integrity. We also trust the host to implement the system, to tell us the time. There are a few things we could do about that. And in the future, we want to move up the stack a little bit and to implement higher level features like suspend, resume, and encrypted network communication. But in conclusion, Haven brings us much closer to what I think is a true utility computing model for the cloud. We're really moving towards a model where the cloud is the utility that is responsible only for providing raw resources like processor cycles, networking, and storage. And it doesn't care and can't see what you do with those resources. And I think in the future we'll say, why would you trust the cloud when you don't have to? With that, thank you very much, and I'd be happy to take your questions.
Hello, John Stallworth. You use public key to do the attestation?
Yes.
That sign?
The details are in a workshop paper from Intel about how they do the attestation. It's a group signature scheme.
No, but who is the owner of the private key? The cloud, right?
Ultimately, the trust for attestation, the root of trust is the processor manufacturer. So ultimately, in this example, it's Intel. You get a certificate chain that takes you back to Intel that says
it's Intel's private key?
This processor is implementing SGX, and the processor issues an attestation that says the initial state at the enclave is some hash. So the cloud provider is outside the trusted computing base for this.
Thank you.
Nathan Dunhan from UIUC. I'm interested in the programming model. So you guys did full legacy applications. Can you contrast a little bit with more small-sized pieces where you wouldn't have to deal with Iago tax or supporting so much system, this type of thing?
That's a perfectly valid thing to do with hardware like SGX. And if you look at, for example, Intel published a couple of workshop papers a year ago talking about different things that you could do with the SGX, and they have some examples of applications just like this, where you have a much smaller TCP. And that's a really useful and valid thing to do if you're willing to factor your application like that.
So what's the motivation for the legacy app then, as opposed
Well,
to...
there are lots of them, and we still want to run them in the cloud securely.
Okay.
So like say, I have a database, it depends on SQL, and I just want to reduce the friction to moving that whole stack into the cloud. Haven helps you with that.
Gilles Muller in IAM. Are there any limitation of the memory size? How do you support memory swapping together with encryption?
The hardware, the size of encrypted memory is fixed. I don't know what it will actually be in a production version of SGX, but the hardware also has instructions for paging, so the untrusted OS can page encrypted pages to untrusted memory and back again. We don't measure the performance overhead of that, of course, because we don't know.
Hello, Xinya, UTexas. I'd like to know what will happen if the cloud provider decided to disable the SGX in BIOS and emulate it in the hypervisor.
The application wouldn't know. The application would still run, but the attestation process wouldn't work. So typically, you would pair this up, and the paper describes one scenario for how you would do this. You would pair this up with, you launch the application, the VHD is completely encrypted. Before it can get access to the key to decrypt the VHD, it needs to do this attestation process. And then the remote user would say, oh, well, this attestation is invalid because it's not a real SGX implementation, so I'm not going to give you the key to decrypt the VHD, so no secrets are compromised.
Okay, thank you.
Sure.
John Criswell, University of Rochester. You say that you run unmodified applications. Is that source level, no source level?
Binary level.
Binary level. So then how do you deal with the fact that the application inside may have system calls using, say, the int80 instruction or the syscall instruction?
So actually, at least for Windows, that's extremely rare. But in any case, that instruction will generate an exception. The exception is vectored back up into the enclave, and we can handle that securely inside the enclave. Essentially, we just emulate it.
Okay, and then
so there's a performance overhead for that, like any trap reflection mechanism.
Okay, and then for other most system calls, then you're just essentially replacing the library that's used for libc, for example.
Yeah.
Okay. Thank you.
Sure.
Kurt Collison, VMware. Is the SGX simulator available?
Sorry, you have to ask Intel for that one.
Ed Bugnoli, PFL. Intel introduced VTX without extended page tables back in the day. And if I understand correctly, now they're introducing SGX without support for extended page tables today. Is that a fair analogy?
What do you mean by extended page tables?
Well, the nested page tables, what Intel calls extended page tables.
Oh, SGX works inside a VMX guest. Is that what you're asking?
No. So when Intel introduced VTX, you had to do the virtualization of the guest physical address space in software through hoops. And then they realized it was actually helpful to introduce a concept of nested page tables.
Right.
Now it seems that basically you have a restricted model where you have an enclave, but the enclave doesn't have a concept of virtual and guest
dynamic
physical
allocation
yes,
problem.
or multiple address spaces.
Oh, so that's certainly true. Enclaves don't support multiple address spaces, and they're only for user mode code.
And why?
Well, if you think, I'm only speculating here, I can't speak for Intel, but if you think about how you would have to do that to include multiple privilege levels and address translation, everything else, with the processor implementing the trust boundary, it's mighty complicated. I think we would like something like that in the long term, but I do think it's a hard problem.
Okay, all right, let's thank Andrew once again.
Thanks.